In this video, we're going to cover some of the standard derivative formulas that we're going to be using throughout calculus and throughout your engineering career. Note that these formulas are standard in the grade 12 Ontario curriculum as well as most curriculums across Canada, so we are going to move through this content fairly aggressively. If you find yourself in the position where this is new for you, I would encourage you as quickly as possible to get into the practice of this, and you can use that either through textbook readings or through the QEng prep site that was available over the summer as well. Those are both excellent resources to go a little more in depth on the concepts that we're doing here and the skills that we're developing here. Many of you will have seen derivatives already introduced as slopes, and you can see that hiding in the definition formulas for the derivative. These are both the root of the idea of the derivative in a graphical sense, where we have a change in a height divided by a change in a width on a graph, and then we ask the question, what happens to that ratio, what happens to that slope as we make the the x step, as small as possible. However, going through this process of a complicated numerator-denominator and then taking a limit gets a little bit tedious after a while. And when we're working with very common functions like polynomials or trig functions or exponentials, maybe nested with other functions inside, it turns out that this practice of calculating limits and doing ratios turns out with certain patterns or returns a certain patterns. And so what we end up doing instead is bottling that calculation up into a more standard notation for commonly used functions. If we have to, we have the definition, but day-to-day practice is simply to apply these derivative rules, pattern rules, to the functions that we use all the time. So what we're going to do now is simply explore that set of rules and build up that skill set of working with functions and calculating the formula for their slopes. Here is your first review of the derivative rules. The derivative of a constant is 0. So for example, if we have the derivative of 5, if you think of 5 as a function, it would just be a horizontal line. What's the slope of that line? It's 0. Polynomials are built out of powers of x to some power. This rule here is paraphrased, at least I paraphrase it as, bring the power down front and then subtract 1 from the power. If you do that, if you say that mnemonic, I find that more intuitive or easier to remember than this more formulaic approach. For example, if we take the derivative or ask what the slope formula is for x cubed, we bring the power, the 3 down front, and we get x to the 3 minus 1, 1 lower power, x squared. This defines the slopes of the graph of x cubed. The next two rules are ones that most people just apply, sometimes that recognizing that it might be an issue. But if we have two things added together, you can take the derivative of each one of them separately. That's totally fine. Same with subtraction. The one that tends to cause grief is if we have a constant but not by itself. The key thing is here, function by itself. Here we have a constant that's multiplying another function, so something that is changing. And there, the rule is we can bring the constant out front and keep it as a multiplier. Keep the constant as a multiplier. This becomes much clearer when we go through some exercises and some practice. For example, we have two things added together, so we can find the derivative of one first, then add the derivative of the second term, the derivative of x to the 4, bring the power down front, and take 1 lower power, so we get x cubed, plus the derivative of 3x squared. This 3 is a multiplier of another function, so it stays around. So we get 3, and then times the derivative of x squared, bring the 2 down, keep the x to the power 1, and we'd usually tidy that a little bit to simply 6x to the power 1. We don't need to show the power. This derivative here looks a little hairier. Fortunately, the first thing we can do is rewrite it in a form that makes those rules easier to apply. And by that I mean write roots and, in general, fractions as powers. So remembering that d dx is the verb, it says take the derivative of all of this. We're not going to take the derivative yet, so we still have the take the derivative of, and then we say x square rooted is the same as x to the 1/2. The pi is fine, that's already as a power. And now we can actually take the derivative because we have written it in a way that is easier to apply the rules from the last page. This 2.6 is a multiplier. This pi is a multiplier, and we'll get to the 4 in a second. 2.6 x to the 1/2, the 2.6 stays. X to the 1/2, we bring the 1/2 down front, and then we subtract 1 from that power. 1/2 minus 1 is negative 1/2, and that finishes that first term because it's then subtracting something else. So minus. Pi is a multiplier of x cubed, so the pi stays as a multiplier, and we bring the 3 down front, we subtract 1 from the power, we get 3x squared. Last but not least though, we have constant by itself. 4 as a function has 0 slope, so when we take the derivative, which is calculating the slopes, we get a 0. Just be aware of that distinction. Multipliers of functions, they stay around. Multipliers of 1 or constants, their derivative is always going to be 0. And then again, we can tidy this up. We're not too worried in the course about simplifying derivatives because it depends on what you're doing next, but some basic tidying of constants like this is just good practice. Whether you want to leave this as x to the negative 1/2 or just recognize that that could be written as 1 over root x as good practice with your handling exponents, doesn't really matter. And there's not much we can do with the 3 pi x squared, except usually the numbers get written before the pi symbol. Now consider the derivative of negative 3x squared minus 1 over x squared. Take a moment to think about these options or do the calculation yourself, and then we'll take a look at it. All right, if we do our derivative calculations, we'll do this the long way. Except the one thing we're going to do is rewrite this as a single power. This is x to the negative 2. So if we're careful with our rules, the negative 3 is a multiplier. The derivative of x squared is to bring the power down front, 2x to the power 1, minus, bring the power down front, applies again here. Subtract 1 from negative 2 makes it more negative, and we get negative 3. And then when we tidy up, we're going to have negative 6x plus 2 over x cubed. We have the negative exponent, so we can write that x cubed in the denominator. Then we can scan down our list and go, we need the negative 6x, that's great, plus 2x cubed. That makes b the correct answer here. The next most commonly used functions after powers of x are the e to the x function and log function, and also other bases, so 2 to the x, 10 to the x, log base 2, log base 10, commonly used as well. For calculus, you can see why e to the x is special. When we take the derivative of the function e to the x, and this is a bit surprising, if we graph it, here's e to the x. It turns out that the way this function is built, and the fact that e is 2.71, etc., 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 that carefully crafted number guarantees that the slope at any point also is given by exactly the same formula. That's a bit surprising, that's a bit weird, or it should feel weird, because values and slopes generally are not this closely related. In fact, the exponential function is special in that it has this relationship. The derivative of the values, or the slope at any point, is given by the same function that you started with. You can see even for other bases that that's not the case. It's almost the same thing. If we have the derivative of a to the x, we get the same a to the x again, but then we get an extra scaling factor of the ln of the base. Now, that actually applies here as well. If you want to, you could write times ln of e and use the same rule, but the ln of e is just 1. So we can't see it when we do the e to the x derivative. This is the general rule, it applies all the time for any base. The e to the x one just happens to be the simpler case because that extra scaling factor disappears. Switching gears, if we have the ln, the natural logarithm, its derivative is 1 over x, not something you'd see coming, proving that's actually a bit of a challenge, but it's a very simple rule to memorize. Same idea with the log of some other base. So if we had log base a, we still get the 1 to the x. So same pattern as the exponentials, you get the same root function, same basic function involved, but then we have the scaling factor this time here in the reciprocal or in the denominator, the scaling factor 1 over ln of a. So recapping, derivative e to the x is e to the x. Derivative ln of x is 1 over x. Those are the main two that we use, but there's their related cousins with a new base, and all they are the same rules, except with a ln a multiplier for exponents and a ln a divider for logarithms. Let's practice with that. Again, here we see some multipliers, the 10 and the 4 here, and then we have the exponential function and a power. So we're trying to distinguish those two. Let's take the derivative of the first term. This is a form of a to the x. The base is constant, the exponent is changing with x, and so we get the same exponent back times the ln of the base. That's our derivative rule for a to the x rules. Then this one here, x is in the base, and what's constant is the power, p. Here's the power 4, so we use the other rule. So we have the 10 multiplier, that stays. Then it's bring the power down front, subtract 1 from the power. And there's not a lot we can do with this either, but we might just tidy it up a hair for that second term, taking the 4 and the 10 and multiplying out to be 40. This example highlights how careful you have to be about where the variable is. It has a huge impact on what rules you use, and only one rule will ever apply at a given time. Similarly here, we have e to the x. Its derivative is just e to the x. If you wanted to, you could include the ln of the base, but we know that's 1, so we'll just erase that. It has no effect. Then we have a logarithm. The derivative of every logarithm is 1 over x. If it's log base 10, we have that scaling factor in the denominator of 1 over ln 10. Now there's not a lot more we can do with the exponential and log rules until we get to the more advanced combination rules like product, quotient, and chain rules, which we will get to and explore these a little further.